Welcome to our lesson that's going to deal with alcohols, ethers, and thiols. These three classes of organic compounds known as alcohols, that functional group of OH, ethers that contain a carbon, oxygen-carbon, and the thiols, which are very similar to alcohol, but instead of OH, they have SH as their functional group. Each one of these three categories of organic molecules will be discussed with the following key questions in mind. What are the structures, names, and physical properties of alcohols? We'll talk about the characteristic reactions with alcohols. We'll look at the structures, names, and properties of ethers, and those structures, names, and properties of thiols in this series of organic lessons. In this chapter, we study that physical and chemical properties of alcohols and ethers. Both of those classes contain oxygen in organic compounds. That study of thiol, as mentioned, is a sulfur-containing organic compound. Thiols, very similar to alcohols in structures, except they have an SH group rather than the OH group. Alcohol is where we'll begin. It will talk about a hydroxyl group as its functional group. To kind of bring a little bit of further information, let me come down just a little bit and kind of give an idea to the content of this chapter. If we take a look at a structure that contains an OH functional group, we'll know that this is called an alcohol. It will be the first topic. If indeed we have a functional group where an oxygen is contained in the carbons, we end up having what's called, let me get those branches in there, this will be known as an ether. And if we have something that contains an SH group, very similar to an OH group, this will be known as a thiol. So these are the three topics that we begin with an alcohol, study its nomenclature, physical properties, and characteristic reactions. We'll do the same for ethers and wrap it up with thiols. Just to give an idea in terms of nomenclature, the root word here for this saturated single bond compound would be ethane. We'll learn that you take off the E and simply add OL to name it as an alcohol. This is called ethanol. Here we will see that this particular structure is called diethyl ether. And over here we'll have ethane thiol, to give just a quick preview of the lesson. But we'll begin with the study of the nomenclature then for our organic molecule family known as alcohols. The compounds that contain OH, a hydroxyl group, bonded to a tetrahedral carbon, that is telling us the hybridization is sp3 with its tetrahedral molecular geometry. It will have three hydrogens bonded to a carbon to be an sp3. So in this particular example, this might be a terminal carbon if it's primary. It might have a carbon attached to another carbon, which would make it secondary, or alcohols could also be tertiary, as we noted in an earlier lesson. The functional group of an alcohol is called the hydroxyl group. Therefore, methanol with one carbon, methane, the single carbon root word, ending with an OL, would be the simplest of the alcohols. The IUPAC names of alcohols are derived in the same manner as those for alkenes and alkynes, with the exception that the ending of the parent group we drop the E and change it to OL. The ending OL will tell us that it's an alcohol. Rule 1, when we name alcohols, we want to find the longest carbon chain that contains the hydroxyl functional group. The OH must be in the parent alkane, and it gets precedence when we're numbering, even if there are other substituents. The OH will always get the lowest number. Rule 2, change the ending of the parent alkane, dropping the E and changing it to OL. We use the number to show the location of the hydroxyl group. And for cyclic alcohols, the carbon bearing the OH is always given the carbon number 1 position. And then we simply name and number any other substituents and list them in alphabetical order, very similar to rules from before. To derive common names for alcohols, there are quite a few that persist in the IUPAC system, but what we'll practice is not only common names, but more importantly the IUPAC name. And here's a series of molecules for an example. Feel free to draw them with me. Here we have 2 carbons ending with an OH functional group. The root word ethane, dropping the E and ending it with OL. The IUPAC name, ethanol. The common name would be called ethyl alcohol. Here is a carbon chain that contains 3 carbons, and in position number 1, that's better, in position 1, that priority of carbon 1 goes to the OH, we're saying that this is 1-propanol or propyl alcohol. Here is a carbon chain that contains 3 carbons and the OH is at position 2. It's a secondary alcohol. 2-propanol. The common name, isopropyl alcohol. This is rubbing alcohol. It might be in your medicine cabinet at home. Here's a 4-carbon chain. Carbon number 1 gets the precedence next to the OH functional group. 1-butanol. If the carbon number 2 has the functional group of the alcohol, it is now called 2-butanol. And notice that we have butyl alcohol or secondary butyl alcohol as their common names. Common names are in parentheses here. Here we have a carbon 1, 2, 3. At carbon number 2 is a methyl. At carbon 1 gets priority, even though these are the same distance from the chain. Priority goes to the functional group of OH. 2-methyl 1-propanol, commonly called isobutyl alcohol. And here's a tertiary butyl alcohol. Numbering here, there are 4 carbons altogether, is why it's tertiary butyl, but you can clearly see you'd have 2-methyl 2-propanol. And cyclohexanol. Notice there is no number needed simply because the cyclo is, that's always assumed here that that's position 1, so we don't need a number. Even if there was a substituent group here like a methyl, we would say 2-methyl cyclohexanol because we automatically know the OH is at position 1. Let's try some. These are coming from examples in our textbook, top of page 399. Let's name the following. Notice it's not asking for common names, but the IUPAC. So I want to find the longest carbon chain that contains the OH, and I want to number from the side that gives the OH the lowest number possible. And I can see that I have 5 carbons. At position 4, there is a methyl group. At position 2, we have the alcohol functional group, the hydroxyl functional group. And since we have a 5 carbon, this would be called 2-pentanol. 4-methyl 2-pentanol. This looks like this carbon that has the OH attached to it has 2 carbons attached. It would be called a secondary alcohol. Here we know we have a cyclic ring in which there are 6 carbons, so I know it's cyclohexane. At position 1, always, we have our functional group, and at position 2, there's a methyl group. Since we have a cyclic structure in which we have one appearing coming out of the page and one going in front of the page, I do see some isomerism going on. We'll have to also mention that it is trans in terms of the functional group location. Trans 2-methyl cyclohexanol. Here we have a carbon Looks like 7 in a chain. At position number 2, we have 2, and that prefix for 7 is heptanol. Here's carbon number 1, 2, 3. At carbon 3, so that's the longest chain I find no matter which direction I go, we have, so that's propanol. And at position 2, we have 2,2-dimethyl, 1-propanol. OL ending for the alcohol. You can probably see this could be considered a tert-butyl function as well, but we're asked to name not common names, but IUPAC names. Shall we try a few more? Let's extend the page and draw some together. I'm going to draw a cyclic structure with 6 carbons. Oh, let's make one coming up, and I'll draw that in, is the OH functional group. And I'll put one here, drawing it coming out of the page, so I'm trying to draw that they're both coming out, so that would be cis, coming both in the same direction. And this functional group will have a structure such as this. So this is all coming out at us. Alrighty, so I notice that just to kind of help number, this gets priority, 1, 2, 3. And here we have 1, 2, 3. So that's an isopropyl functional group. And I see that it is cis in terms of isomerism. So at carbon number 3, we have an isopropyl functional group. And we simply finish it by saying cyclohexane. Cyclohexanol, thank you. Cyclohexanol for the functional group OH. And those are the solutions that we worked to the previous one before I made it up. Let's practice in the following. Let me just kind of go back before we look at this slide. I'd like to take a look at something else while we're looking at these in terms of just an additional practice in terms of, is it primary, secondary, or tertiary alcohol? So classifying primary, secondary, or tertiary, just to help us remind ourselves, primary alcohols, we have the carbon that has the OH just attached to one other carbon, primary alcohol. If it's secondary, the carbon attached to the OH, maybe I'll draw it up, has 2 carbons attached to it. And if it's a tertiary, the carbon attached to the OH would have 3 carbons attached to it. So this is just asking us to consider, are the alcohol structures primary, secondary, or tertiary? Well, let me draw one for us. Let's draw in, well, let's put an OH here. And I counted 1, 2, 3, 4, 5, 6, 7. So there are 7 carbons, so I know it will be a heptanol. And at carbon 2, we saw the OH position. Is this a primary, secondary, or tertiary alcohol? Well, here is the carbon that has the OH attached to it. It indeed has 1, 2 other carbons attached to it. It is a secondary alcohol. Suppose we see one. Well, let's just draw. We'll put in OH. That's not a very good bond angle. It should be over to the left more, but we'll get the idea. This will be carbon 1. Very long tail, bad drawing. Carbon 2, carbon 3. And I can see 2,2-methyl coming off. But again, we're just practicing, is it primary, secondary, or tertiary? So here is the carbon that is attached to the OH. It is only attached to one other carbon, so it is a primary alcohol. And how about if we see a cyclic structure? Cyclohexanol. Again, I'll just put the OH here. And I can come down and simply try that functional group again. We'll make this cis, draw this earlier and named it, and we had the isopropyl group coming off of it. But again, numbering for primary, secondary, tertiary, here's the carbon that has the OH attached to it, and therefore I count 1, 2, it's also secondary. I'll try one more. Here's a carbon chain, OH, we'll put a methyl here, so these are all methyl groups. And if I count, here is the carbon attached to the OH group, so I have 1, 2, 3 carbons attached to the carbon attached to the OH. There is your example of a tertiary alcohol. In the IUPAC system, a compound containing 2 hydroxyl groups gets named as a diol. One containing 3 hydroxyl groups is named as a triol, and so forth. In IUPAC, the names for diols and triols do keep the final E from the original alkane ending. That E is retained. For example, here's a 2-carbon chain. Each one of the carbons has an OH group. It's a diol. At carbon 1, 2, carbon 1 and 2, ethane diol. And this has a common name, ethylene glycol, which is radiator fluid we place in the cars to help keep the engine from flowing and freezing up in the wintertime. It's a coolant. Here we have a 3-carbon chain. At carbon 1 and carbon 2, we have the OL grouping. So 1, 2, propane diol, propylene glycol. And then a 3-carbon chain where all 3 of them create the name 1, 2, 3, propane triol. Some people make rock candy with something called glycerol or glycerin. It's a very thick syrupy fluid, very similar to Caro syrup you buy at the shelf at Meijer if you're a baker. So again, we'll just keep the final E and just simply name as a diol or as a triol, numbering the position of the functional groups. The most important physical property of alcohols is their polarity from that functional group OH. There's a very large difference in electronegativity between oxygen and carbon and between oxygen and hydrogen, and therefore we set up a polar region of the bond. You can clearly see that this particular section of the exposed electrons is left as a little bit negative, and of course the exposed hydrogen and even that carbon would be a little bit positive. So this region right here is extremely negative. And this is going to meet the criteria as well for the intermolecular attraction known as hydrogen bonding, one of the strongest of the van der Waals forces. Just a little side note, van der Waals forces contain dispersions, they contain dipole-dipole, and they contain hydrogen bonding. And we can see that increasing in strength as we go down the list. Dispersion forces exist between all molecules at temporarily induced pole, but they are indeed the only forces for nonpolar. Dipole interactions occur between polar molecules, and hydrogen bonding, the strongest of the intermolecular attractions, occur between OH, ON, and OF. Oh my goodness, I've just said that wrong. Hydrogen bonding, please forgive me, I need to straighten that up, will occur between HF, HO, or HN. That's the criteria for a hydrogen bond, of which you can clearly see this does indeed meet the criteria, an OH group. So you can see, just as a water molecule is extremely polar and sets up interactions of hydrogen bond, so does these alcohol functional groups. And these again are very miscible in one another. Alcohol dissolves quite readily in water due to the hydrogen bonding interactions. So hydrogen bonding deals with things such as very high boiling points for the alkenes or alkynes. If they had similar molecular weights, alcohols will boil much higher, take so much more energy to overcome these hydrogen bonds than a simple dispersion force. As the hydrogen bonds interact with water molecules or interact with each other, they set up a very strong intermolecular attraction, making the liquid state more stable at room temperatures than some of the gases we have for, equivalent formula weights, molar masses, if you will, for alkanes, alkenes, or alkynes. As alcohols increase in their carbon chain, however, we start to see that the dispersion forces will take over. So let's take a look at this chart. Here we have a simple alcohol called methanol, nothing smaller than methanol. Very similar formula weights to ethane, and yet look at the significant difference in boiling point. Methanol boils much higher as compared to something similar in formula weights. Same is true here. Here's ethanol, ETOH, ethanol, boiling at 78, whereas a similar structure of equivalent formula weight at -42. And you see that the trend is increasing. The heavier the molecule becomes, the more that the dispersion forces play a role, and we know that increased formula weight also raises the boiling points. So eventually, as these chains get longer and longer and longer, very long hydrocarbon chains, what you'll also start to notice is that the solubility in water begins to decrease. Whereas we have infinite solubility of very low molecular weight in water, by the time we start getting longer and longer carbon chains, this non-polar region is more difficult to get to dissolve into a small structure of water, and you start to see the solubility decline. So the heavier, longer chained alcohols do not dissolve in water as readily as the smaller, lower molecular weight alcohols. Let's talk about those characteristic reactions of alcohols. In this section, we'll look at the acidity of alcohols, their dehydrations to form alkenes, and their oxidations to form aldehydes, ketones, and carboxylic acids. Two of these three are review from previous lessons, but now we'll go in the opposite order. The first one talks about the acidity of alcohols. Alcohols have about the same pKa value as water. When I interpret that, the pH of water is 7.0. That's not very acidic. It's not basic. As a matter of fact, it's neutral. Alcohols are going to follow that same pattern. Aqueous solutions of alcohols have the same pH as pure water, neither acidic nor basic. However, alcohols react differently than phenols. In our last chapter, we had a chapter that discussed benzene and its derivative. One of the derivatives is known as phenol. Notice this is an aromatic alcohol. The aromatic alcohol will be slightly acidic. This aromatic ring, known as benzene, behaves differently than the aliphatic alcohols that this particular chapter will deal with. Let me write that word. Aliphatic. Those are either the alkanes, alkenes, alkynes, or cyclic structures, anything but the aromatic compound. The aromatic functional group is slightly acidic, so this alcohol functional group of phenol will react with a very strong base, and we talked about this in the last section. Acid plus base neutralizes each other to make a salt and a water. We said right here that it's nothing more than a double displacement. H goes to OH, and A comes here. And in that substitution, we have water as the driving force, and sodium phenoxide is a water-soluble salt. Keep in mind, even though this is considered an alcohol, it's an aromatic alcohol, which makes it slightly acidic, which will acid-base chemistry. These aliphatic alcohols that we're discussing in this chapter are neutral. They behave like water. They're much, much weaker, and therefore we do not see a reaction occur with a base. So there is no reaction. They do not behave in this manner. So just kind of keep a heads up. If you see an aromatic compound, it is an acid, slightly acidic, acid-base chemistry will occur. If you see just a plain old cyclic structure, and you see it trying to react with a strong base, nothing will occur. An acid-catalyzed dehydration of alcohols is our next topic. We are able to convert an alcohol to an alkene by eliminating a water molecule. That's the process known as dehydration, elimination of a water molecule to form an alkene. Well, I remember in the alkene section, and we'll just kind of bring it down to the bottom, we talked about hydrolysis, and when that hydrolysis occurred and we had a catalyst involved there, we opened up the bond and placed on an OH group. We added HOH, breaking the double bond. So this is something that should be familiar to us from a similar lesson, the hydrolysis of an alkene, representing a chapter, I think it was 2 chapters or so ago. So now we're going to look at it in the opposite direction. If I take an alcohol and dehydrate it, subtracting out the water, we go on to produce the alkene. These really are competing reactions, reversible in many ways. In the laboratory, dehydration of an alcohol is most often brought about by heating it with a strong acid, such as 85% phosphoric acid, H3PO4, or concentrated sulfuric acid, H2SO4. Heating that with a catalyst, kind of coming down here in the overall general view, allows us to dehydrate. What we'll do is subtract out an HOH and bring back the double bond. Primary alcohols tend to be the most difficult to dehydrate. So what you'll see is a very high temperature in addition to a very concentrated acid. Secondary alcohols undergo it a little bit easier, so you don't need such a high temperature. And tertiary alcohols quite readily undergo acid catalysis of dehydration, so really just slightly warm, slightly above room temperature, and those reactions occur quite readily. Let's take a peek at some of the structure in a dehydration. Here's an alcohol called ethanol. Notice it's a primary alcohol, so the temperature is very high, 180 degrees Celsius. We're using a catalyst of sulfuric acid. And if I just think about this structure, we have CH3, CH2OH. So if I just take a look here, this hydrogen and this hydroxyl functional group is going to come together to make the water. So I'm eliminating one bond position from each of the carbons, and there's the double bond that forms. An elimination of water is called a dehydration. Here we have an example where the carbon containing the OH is here. And again, just picture either side of these we have a hydrogen, so that's the same structure in either direction. But this is called a secondary. If this was a primary, here I have a secondary alcohol. The carbon that contains the OH is indeed attached to 2 other carbons. Notice how that temperature is a little bit lower. This happens a little more readily. And we go on to form cyclohexene. Here's an example of a tertiary alcohol, 2-methyl 2-propanol. The carbon that is attached to the OH is attached to 3 other carbons, and notice the temperature is about 50 degrees Celsius. Just kind of reminding us that it's happening more readily. And again, taking the OH removal, and you can see the product becomes an ethene. Now, when I structurally think about that, this H or from this side, I really would have a choice there, and you'd have just a couple different isomers as possible answers. 2-methylpropene and water have been produced. So the ease of dehydration, primary are more difficult than secondary, which are more difficult than tertiary. So the ease increases, so this would be the most difficult to the most of ease. When the acid-catalyzed dehydration of an alcohol yields isomeric alkenes, the alkene having the greatest number of alkyl groups on the double bond generally predominates. Now let's examine that statement. Here we have an example of an alcohol called 2-butanol. 1, 2, 3, 4 carbons in our chain, and on carbon 2 we see the alcohol. Now thinking about that, I'll just come down here and draw the structure for us. And here's the H, CH3. How do we go about predicting if the double bond, when I remove water, will go here or here? What's the best predictor? Well, it goes back to this statement that says the greater number of alkyl groups on the double bond will dominate. So let's draw both possible answers and decide the best of our two. If indeed we take off the H here and form a double bond, here we go, and we end up with CH3. Here is the structure of one possible answer where we removed the OH and the H from these two adjacent carbons. Or suppose we removed and formed a double bond here, removing the H and OH from these two adjacent carbons. What would that structure end up looking like? We'd have this as the other answer. These are called isomers. They have the same molecular formula, but they are attached in a different order. Which one of those will generally predominate? Find your double bond in the structure and see indeed which one of those has a greater number of alkyl groups. More carbons coming off of the double bonds is all that that's saying. So if I think about that, oops, I've lost my spot. Sorry. Patience for me, please, as I find that slide. "13, 14 must have been here. Sorry. So as we come down on this slide, we're looking at the predominant being this one, where we indeed have both of those bonds being shown. Now I've lost all my slides. There I have it. So thank you for your patience. We worked through that little glitch, but what I was trying to do is to show that indeed this one would predominate because I have two carbons on that double bond, whereas over here it terminates, and that's not the favorable position. Same could be true here. We have 3-methyl 2-butanol, and we're just looking to see how the predominant structure would indeed form. So if I removed, here's the carbon with the OH, I could form the double bond between this or between here. And again, you see What predominates is placing the double bond further into the chain rather than at the terminal end. It favors the position that has more alkyl groups on both sides of the double bond. So 2-methyl 2-butene would indeed be a favored structure over 3-methyl 1-butene. We mentioned that dehydration and hydration really are opposites of one another. Acid-catalyzed hydration of alkenes to give alcohols was studied in Chapter 12, our alkene-alkyne chapter. If I took the double bond and underwent a process called hydrolysis, we added water, HOH. And in this chapter, we're reminding ourselves that if we change conditions, we can reverse the reaction and take off the water molecule and go back to the alkene. In the equilibrium study of Le Chatelier, we see that if there is an increase of water as a stress, the equilibrium would push right and the alcohol is favored. If we have a situation where there's low water, Le Chatelier would predict the equilibrium shifts left and we would favor the alkene. So a little reminder of Le Chatelier. A third category is known as oxidation of primary and secondary alcohols. Oxidation of a primary alcohol gives an aldehyde, and if that reaction is allowed to continue, it would go on to form a carboxylic acid. Let's remind ourselves that oxidation is either defined as removing hydrogen or it's defined as adding oxygen. By removing hydrogen or adding oxygen, we've had an oxidation occur. Remember, the opposite of oxidation is reduction. Reduction adds hydrogen or removes oxygen. So kind of thinking in lines of a review term. The oxidation of a primary alcohol would yield an aldehyde by removing a hydrogen. If I continue with the oxidation process, it will yield a carboxylic acid. In an example, suppose we have an 8-carbon chain, such as this, 1-octanol. And notice it's just a primary alcohol attached to 8 carbons, but here is the OH group. The catalyst is potassium dichromate, K2Cr2O7. On our polyatomic ion chart from inorganic chemistry, we had dichromate. And of course, potassium, who carries a +1 charge, we would crisscross charges and we get this salt, potassium dichromate. It's a purple solid found in most labs. In the presence of a sulfuric acid catalyst, again the aqueous medium, being acidified with potassium dichromate. Notice here the hydrogen is going to be removed from the terminal carbon. And so now we come up with what's called an aldehyde, a terminal carbon with a double bond. And if I continue the reaction, I can go on. Now notice here, this from position 1 to position 2, this is called an oxidation because we removed hydrogen. Step 1 is removal of hydrogen, and now we create an aldehyde. In the next oxidative process, we add oxygen, and adding oxygen goes on to form this functional group, COO, the carboxylic acid, COOH. Step 1 of a primary alcohol produces an aldehyde, and if we continue with the process of potassium dichromate sulfuric acid catalysts, it will continue the oxidative process by going all the way to form a carboxylic acid. Notice that this can only happen at a terminal carbon, so this process can only occur with primary alcohols. Primary alcohols have their alcohol at the end position attached to only one other carbon here. And so therefore, the correct nomenclature of a terminal carbon functional group is an aldehyde. And at the terminal carbon, if we add on the OH, we get a carboxylic acid. If we oxidize secondary alcohols, the correct term is known as a ketone. Here is the carbon that contained the OH. It's attached to two other carbons, and so it is properly called a secondary alcohol. And if I remove hydrogen and form a double bond, removing hydrogen is one way to define oxidation. You produce this functional group called a ketone. You cannot go on any further in a secondary alcohol to form a next step that's unique to the primary alcohol position. Tertiary alcohols, here is a carbon that has the OH attached to it, and it contains 1, 2, 3 carbons attached to the carbon attached to the OH, so it's a tertiary alcohol. They do not undergo any oxidation. There is no H on that terminal carbon to remove to form a double bond, so no oxidation. So very interesting, very selective oxidation process. Primary alcohols undergo a two-step oxidation. Step 1 to an aldehyde, step 2 to a carboxylic acid. The same set of conditions form from a secondary alcohol will remove hydrogen and produce a ketone, and that's the end of the story. And in tertiary alcohols, there is no hydrogen readily available to remove, so therefore no reaction. Tertiary alcohols cannot be oxidized. Let's add a few slides and just practice some of these skills. Let's suppose I'm going to just draw a hydrocarbon chain. 1, 2, 3, 4, let's do 5 in a row. I'll place a methyl group up here, and how about at position 3, the OH group. Alrighty. And what we'll do here is add the catalyst of sulfuric acid. So this would be an acid-catalyzed dehydration. What are the possible isomers that would form and which would be predominant? Here is the carbon that's attached to the OH. Should we properly form the double bond going this direction or the double bond going in this direction? That's what we're being asked to solve for. And remember the rule that suggests the double bond is going to favor forming in the direction that has more alkyl groups associated with the double bond. So let's do choice 1, C, 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 double bond C, and then here's the other two carbons. There's choice 1 between these two carbons. Here's choice 2, C, C, oops, that's not there, that's an H. I'll just erase that so we don't get confused. I'm only drawing carbon structures. So here's the beginning, but now we'll have a single bond, double here. So here's choice number 1, here's choice number 2. Which one will be more dominant, more prevalent in the reaction? Well, again, I can clearly see that this particular structure has more alkyl groups associated with the double bond, and this will indeed form the major product. I have 3 carbons on this side and an iso group coming on this side, so that definitely has more carbons associated with both sides. Let's see. Just trying to pull examples from our book. How about from an oxidation process, we draw 1 hexanol, 1, 2, 3, 4, 5, 6, and then an OH group. 1, 2, 3, 4, 5, 6, then you could put your OH there. So there's the same structure, draw in line or draw in with carbon bonds. And we want to oxidate. So over the arrow, what you typically see is just a process of oxidation drawn in a bracket. When you see that, that's just simply saying it's being oxidized. Well, what will happen? First of all, I notice that this is a primary alcohol. So therefore, my first oxidative process will produce something called an aldehyde. So when I produce my first product, 1, 2, 3, 4, 5, 6 carbon chain, and at the terminal carbon, I have the aldehyde functional group. The first oxidation of a primary alcohol produces an aldehyde. Typically, if you choose to stop the reaction here, you could do so by the process of distillation. If you indeed keep the reaction going and undergo further oxidative process, remember that typically it's potassium dichromate with sulfuric acid that's going to perform this for us. What structure will it now make? Well, we'll still have 1, 2, 3, 4, 5, 6 carbon chain, but now we go to the carboxylic acid functional group. A primary alcohol in a two-step oxidative process first becomes an aldehyde and then goes on to carboxylic acid. Suppose we just go 1, 2, 3, 4, 5, 6, and then here's our OH. So again, let's make that different. Let's say, let's put the OH up here and make this a secondary alcohol. Through the oxidative process of potassium dichromate, K2Cr2O7, and concentrated acid, we undergo oxidation. Well, in this process, 1, 2, 3, 4, 5, at this point, we will form a ketone. And the reaction stops. There is no next step in an oxidative process. We simply remove hydrogen. Excuse me. In the previous example, we removed hydrogen to create the aldehyde, and then we add oxygen to make the carboxylic acid. Both of those indeed meet the criteria of being defined as oxidation. Let's pause our lessons here and give you time to digest this material so far. Practice your skills with nomenclature of alcohols and practice your reactions with alcohols. And when ready, start the next lesson.